Ok, empezamos entonces.
Sí, estamos en la hora. Yo sigo admitiendo mientras hablas tú.
Yeah. Welcome everyone to COIM. My name is Rodrigo Castillo, and as the director of the organizing committee, I would like to thank all the people that helped us to make this event possible, especially to our speakers. Even though most of them are pretty busy people, they were willing to take some time to talk with us about their projects. And to our audience, of course, these 3 days belong to you, and I hope that you get the most of them. That our students can learn more about some of the many areas in which they can contribute as engineers to the development of science, technology, and society. That our speakers can have fruitful discussions with other experts and hopefully to develop the linkage needed to collaborate in the future. For most of us, this is the first time that we participate in an online conference, but for now, life has changed in many dimensions and we have to adapt. That's how, as engineers, despite the circumstances, we can keep looking for solutions to the problems of today and tomorrow. Thank you very much. Fabián.
Okay. Thank you, Rodrigo. Gracias a todos los participantes. So, our first speakers will be Dr. Thomas Davey. He's Senior Experimental Officer at the Flowy Ocean Energy Research Facility at the University of Edinburgh in Scotland. He did his master and PhD from the same university, and his main interests are marine renewable energy, and he likes a lot to work in the interface between academia and industry. So welcome, and you can start, Thomas.
Okay, well, thank you, everyone. It's a pleasure to be here. This is all very new to me. Despite my custom background here, I am sitting at home. We are currently not allowed to access the laboratory, but hopefully over the next half an hour, I can give you an interesting overview of the work that we do at Flowy, and then my colleague Roman is going to cover some of these projects in some more detail. So yes, thank you very much. I'll just try and share my screen. Okay. Hopefully that is appearing now. So please let me know if there's any problems. So what I will do is, first of all, I should just say Flowy is a scale test tank in Scotland, in Edinburgh, where we mainly test renewable energy devices. So I will just essentially run through the operation of the facility and give some examples of the projects we do before Roman goes through some of those projects in some more detail. I'll skip the introduction, thanks to Fabian's kind words. But just to say, I've worked at this facility since 2013. I worked on other tank testing projects before then. So hopefully I've had a fairly good experience, or a fairly wide experience of testing projects over that time. But to step back even further, let's go back 40 years. This work really comes from the work that was conducted starting in around 1973, 1974 at the University of Edinburgh, which was a group called the Edinburgh Wave Group, or Edinburgh Wave Power Project, which was developing very large-scale wave energy devices. And this is still relevant to this day because although this device never came to commercial fruition, the technology that went alongside it fed into the development of very sophisticated wave tanks. And that's really where we come from. So you can tell that the photo on the left here goes back some time. I think this was early to mid 1980s. And this is the Edinburgh Wide Tank. So this was the first big wave tank in the University of Edinburgh. And there was a lot of very important research conducted in this tank because it was very good at developing multi-directional sea states, so very complicated sea states. And they were testing scale models of those of their wave energy design concepts. The process has changed now because we don't really develop the technology ourselves. We develop the testing techniques and we develop supporting technologies. And instead of developing devices, the university and also a company called Edinburgh Designs Limited, who who have connections to the university going back many years, now develop very sophisticated wave tanks. So on the right here, you will see the what is called the Edinburgh Curve tank. And this is what you're seeing here is first generation and second generation. And this is a much smaller facility. The wide tank no longer exists, but this smaller facility was really exploring the concept of how you can use curved tanks and circular tanks even to develop, basically give you much more control over wave direction. And that takes us to where we are now, which is Flowy. So that's a fully circular wave and current tank. And to explain this in a bit more detail, hopefully my internet bandwidth is good enough for this video. Please let me know if there's any big problems. But this animation is quite useful because it shows a lot of the elements which are now hidden within the tank. So if I can get a pointer. So what you have is, obviously it's a circular tank. You have these wave makers around the edge. And what it allows us to do is generate a wave from any direction. So the wave makers are their flaps. These flaps are moving. They're generating a wave. The wave travels across the tank. But they are wave energy devices. I'm just going to get rid of this spotlight, so I think it's slowing down the video. Okay. And importantly, we can also generate current in the tank. So wave current, and this is where the unique design of the tank becomes very important. So this is the only large circular wave and current tank in the world. So the current travels underneath the floor, so you have this recirculating effect. So you've got this bank of propellers underneath the floor, and they're arranged in a circle. So we have a circular arrangement of propellers and a circular arrangement of wave makers, and by combining them, we can generate the waves independently from the current. So we have independent control of the wave and current direction. And this is really important, first of all, for wave directionality purposes. So I'll just try getting that pointer. Right. So what we're interested here is, without going into the detail, this, for those of you who don't come from a wave background, this is a directional spectrum. And what we're looking at is the direction that the wave energy comes from. So what we see here is we've got two peaks, one here, and that's showing us that we have a peak of wave energy coming from 180 degrees approximately, and another peak coming from 285 degrees. And by being a circular tank, it gives us the ability to not have any restriction on modeling seas like this. So we can add wave energy coming from those different directions. And in a similar way, without getting too much into the detail, we can do the same with current direction. So you can do a lot of work with current just by having a tank which can generate that flow in two different directions. But what we can do in Flowwave is start to have angled flow. So in this particular example, we have, this is showing a tidal ellipse, so how the direction changes over time. What you can see in the ideal version is we go from a maximum flow here with these directional components at 0 hours, and then we travel all the way to here to the opposite at plus 6 hours. But as we pass through this, we don't ever quite get to a zero current speed. But what we have in reality is a much more complicated arrangement when we look at real measurements, and sometimes we don't even get a 180 degree shift. So what we can do is actually model very realistic changes in current direction. And this becomes important. I don't know what the resource is like in your local areas for everyone watching, but in Scotland, we have very fast. We have a very fast site called the Pentland Firth, which sits between the Scottish mainland and the island of Orkney. We get very fast current velocities in here, and you can get very complex directional behavior in these sites. So, how does that look like in reality? So the tank operating. Roman and I were joking about this earlier because the tank is very tidy. This was a video taken a long time ago. What we see on the right is wave makers generating. So those paddles you saw in the video, and the wave travels across, and then it's absorbed on the other side. And then we can do this from any direction and then build up very complicated sea states by combining these waves. And same idea, but for the current. Here we see the current at 1.2 meters per second. Doesn't look that fast in the video, but this is actually a very fast current velocity for a big basin like this. If you want to scale it up, this would be about 5 meters per second for a full-scale site, which represents something like the Pentland Firth, which typically is about 4 meters per second. So it's got plenty of overhead for doing very fast velocities. And then things become exciting when you put the two together. So we combine the wave and the current. We see the current is traveling into the screen here. The wave is coming back the other way. And what you'll see is the current changes the wave quite dramatically. So that wave starts to steepen up and it starts to break. And this is quite a dramatic example because we're dealing with quite fast current speed. But even quite low current speeds can cause quite a dramatic change in the wave behavior. And that can be very important when you're trying to feed in the conditions from a real site. So why do we do all this work? Just to step back a moment, we're really interested in our university and in our school on how we tackle all the problems associated with offshore renewable energy. And for those of you who perhaps come from a background where you're not familiar with this, we're really dealing with wave energy devices. And these can be of lots of different designs here. A hinge raft, for example, buoy type devices. You can get seabed mounted devices, which aren't shown here. Interested in tidal energy, typically seabed mounted, but there's lots of floating designs as well. And a growing area is offshore wind. So vast majority of offshore wind turbines to date are seabed mounted, but now there's a big expansion in looking at floating designs, and that's where wave tank testing becomes very important again. And then we've got everything associated with that, which all our work feeds into, elements like the electrical grid connecting these things, reliability of the cables, the maintenance side of it, and then there can be quite a lot of work as well within the university on all the policy side that goes with that. So this graphic I took from a UK project called SuperGen. So for those of you who are interested, you can find much more information on all these elements and how all this research combines together. And just to very quickly say, to put this in context, what we're really interested here, we can go all the way from very conceptual designs into much bigger laboratories, which is what we are. So we usually start in our small tanks and something like this, the conceptual designs, move into something like Flowy, where we start to look into more complex behavior. How does the generation system work? How do you control the device? How do you get into all the detailed design? And then finally, we sort of leave the lab and go into small scale deployment, but you're sort of still involved at the stage. You might still be doing some element of tank testing, and then it leaves the lab and it goes into large scale deployment at sea, and then finally the commercial device. So to give an example of that, this is something which is sort of lying in between those concept designs and something a bit more advanced. The concept side is because this is a very novel design. So what we have here is what's called an oscillating water column. So the air, the wave is driving the air in the column. And what's unique here, or what's clever, is we are driving the membrane on the top surface. So this is a dielectric elastomer, and it basically works as a capacitor. So there's a charge put across the top and bottom surfaces, and the changing curvature generates a charge and generates power. And in the tank, this is a few watts, but actually this is about 500 kilowatt device in reality. So very conceptual, probably 10 years, if not 20 years away from actually being in the sea. Potentially giving you a lot of advantage in that you remove a lot of hydraulics and perhaps components which are less reliable from your design. A very conceptual design. I thought I'd put it in. I had the pleasure of visiting the test tank in Valdivia last year, and here we have a really good element of the kind of thing we'd measure at a concept stage. So the lab kind of built a very generic flap type device for our tests. And what you're measuring here is you're not worried about things like the generator performance. You're interested in measuring the hydrodynamic. So one of the main things we're measuring here is the movement. And what you'll see is the cameras around the edge. These are motion capture cameras. I think Roman experiments show a bit more of this later. And we have these markers at the top. And then when we play that back, we can then isolate the movements of the device. So we're actually measuring the movement of the device, and that's very useful when you're going then to feed that into something like a numerical model. So to flip back to Scotland, we have exactly the same technology within the Flowy test tank. And here we see these measurements overlaid over the top of a model. This is a company called Anaconda who came to test with us under our Wave Energy Scotland scheme, which is a government scheme. And what we have is we're measuring the movement of this element here. What's important about this is getting to a stage where we're starting to measure not just the movements, but we're measuring the power output as well. So this device works by generating pressure waves in a rubber tube. And those pressure waves are then used to drive a generator, which is located here. Sorry, you can't see my pointer, but it's located in this, this sort of main section with the cables running to it. So another device which was tested under that scheme, and this is quite a nice video because it shows a lot of elements of the facility, is a company called Quotient. And this design here is nice because it's showing a big feature of the tank, which is that it's very important to have repeatability. What we're doing here is the client is removing foam sections on the side of the model. And in real life, this floating wave energy device would be changing its shape using airbags. And what we're doing is running exactly the same sea over and over again. So we have this random sea state, but it's really pseudo-random in that it's completely repeatable. And so we can do back-to-back comparisons with the different geometry. Again, you can see the motion capture camera system, and you can see that we can raise the floor in order to access the model and make modifications. So we can do these changeovers very quickly. And then just to go from the tidal energy side, this is a very fast run through, I know, but just to switch to tidal energy, I thought this was quite a nice example. This was one of our first tests, I think, in 2014. One of the challenges with tidal energy is actually mounting the rotors, mounting the generators on the seabed. So this company is an Edinburgh-based company called QED Naval, and they came to us with a design which essentially is a foundation structure which generates downforce and allows the device to be fitted on the seabed. And the nice thing here is it's showing the stages of development really nicely, because in these early stages, they're not so interested in the power generation, they're interested in the general performance. So what you see is, instead of having lots of complex hydrodynamically modeled rotor blades, it has these discs which generate drag, but it allows them to concentrate on their main bit of work, which is the actual structure. And then that goes from the tank into small scale tests in the sea. And finally, recently, they've got that in the tank. So you've got in full scale in the sea. So there you see that sort of 5-year journey from the concept stage to something full scale and real. The other side of the tidal energy work is maybe a bit more academic. So these generators you see in this picture were actually constructed in-house by a researcher called Dr. Gregory Payne. He designed these devices, loads on the individual turbine blades. So they're very clever in that they're not designed to be a model of a particular commercial design. There's a lot of learning that can be done here, which can then feed out into the industry. And this is very typical of the work we do in the university, because we're not generating commercial intellectual property. We're usually generating knowledge which the whole industry can use. And to give an idea of how these are operating, the nice thing about this design is you can deploy multiples at a time. And in this case, we're interested in how the middle turbine generates, because the middle turbine is getting an accelerated flow from the two outer turbines. And in this test as well, we've got the waves going over the top. Because tidal energy devices are usually in quite shallow water, the blades are quite prone to wave loading effects. They're only maybe 10 meters beneath the surface, if that. So what we can do here is actually measure individual blades, measure the force on individual blades, and understand what kind of loads that's putting into the system. That can affect things like bearing wear, but also power generation performance. And the final part of the sort of three elements is the floating offshore wind side. This is a company called Ocean, who are a Spanish company who tested with us in 2015, I believe, if my memory is correct. And again, you see a good example here of the idea of making a floating type device. So the advantages in a floating device are it lets you access deeper water, also potentially has advantages for construction and deployment, possibly cheaper to actually moor to the seabed. And again, this is a nice example because this floating device, and in this case, we're measuring mainly measuring the movement, but also measuring things like the loads through the mooring lines. The nice thing about this is this now exists in the sea as well. Not yet at full scale. I think it's 1:6 scale at the moment. So again, we've seen a nice journey there over a period of about 5 years, and we still work with that company. So hopefully they continue to be successful. And just to step back from the actual technology before I hand over to Roman, is just to have a look at how all this fits in to the general research landscape. Here we're looking at the physical simulation side. Let's see if I can get my pointer back. So test tank is sitting in this area here. And what this diagram tries to do, you can see a link to the paper if you're interested, is trying to see how we combine that with all the other elements of research. So an obvious one is that the physical simulation connects to the numerical simulation, and you use the results from the physical simulation to validate and improve that numerical simulation. But what we're very interested in the university is moving from measurement data. So we go all the way from what happens in the field, what do we actually measure in the sea, looking at hydrodynamic models, not of the devices, hydrodynamic models of the resource. So for example, a hydrodynamic model of the Pentland Firth in Scotland. And from that, we decide what do we need to characterize that. So what we're using to describe that site, that includes wave, current, but importantly for us, what happens when the two are combined. And finally, turning that into a reasonable number of parameters, which we can then feed into our physical simulation. And the measurement from the field, which I'll only touch upon, a lot of this work is done by my colleague Brian Seller, is a combination of measurements taken from a tidal turbine, for example. We've got beams measuring both the current and the wave field. And then from there, we get very large data sets. And so the interesting process is how we go from these very large data sets, either from those measurement devices or wave buoys, for example, which are floating on the surface, how we then process that in a sensible way. So we describe the statistical parameters. We go through a data reduction process to produce a set of representative sea states. The point being, we could have 10 years of data here, and we need something we can test in a day in the tank. But from there, we go through that process where we can create this link between them. So I had a student, Sam Draycott, who's gone to lots of successful other projects. He did a PhD with us where he was looking at this process. How do we create this link from the resource into the tank? And then finally, how do we validate that? So we do a lot of work on measurement. Here we have a floating measurement, sorry, not floating, we have a wave gauge measurement array. And from this, we're generating quite complex sea states. So again, without going into the detail, we have wave spectrum here, which is describing the distribution of energy in terms of direction. So for all these examples, or certainly this example I'm pointing out here, has two directions oppositely opposed. Here we have a very spread direction, so the energy is spread over a very large area. And in this one, we have two distinct peaks. And then this is what we're asking the tank to do, and this is what we're measuring. So it's a little bit noisier, but you see we're getting the same basic information. And just to concentrate on the bottom left, this one is quite interesting because what we're looking at here is two angled sea states. And we have two sea states coming from different angles. We become quite interested in what happens when they cross. So there's quite a lot of interest in crossing seas because when we get that focusing effect, it could be one of the influences behind freak wave generation. And Sam in our institute and cooperated with or collaborated with the University of Oxford to do a very interesting paper where they looked at this, and they were looking at how freak waves are generated by crossing waves, which is a very nice science, but also got us into the newspapers because it turned out it looked very much like the famous Great Wave. So we got lots of coverage in local papers. So I will just end with our most famous freak wave. I think I'm going to hand over to Roman now. I think is the plan, and I will be available to take questions later in the session. But I'll just leave you with this to end. So thank you very much for your attention.
Thank you very much to you, Thomas. It was a really nice presentation, and I'm sure everybody is clapping in their house, but you cannot hear it. So as Thomas said, right now we will continue with the presentation of Roman Gable, and after that we will be receiving questions from the audience. So al final vamos a recibir las preguntas de las dos presentaciones. Thomas se va a quedar aquí. Y okay, so with you right now we'll start Roman Gable. He is his main studies are from the University of Innsbruck in Austria. Later, he makes some postdoc in Austria and Italy. And right now, he's a research associate in floating energy at Flowy at the University of Edinburgh. With his main research has been in hydraulic engineering and renewable energy. So with you, Roman Gable.
Thank you, Fabian. Yes, good afternoon or good morning in your time zone. It's good afternoon in Edinburgh. I will go through three short examples. Tom covered a lot of different tests we have done, but I want to dig into three ones in more detail. This will be the first one would be the example about a floating cylinder in the wave tank. Then I go back to the floating wind turbine, which will be a little bit deeper into the tank. And then we dive fully into the tank down there with an ROV. What is it about? So the floating cylinder will have only waves. The floating wind turbine will have waves, but also a little bit of current. And obviously the ROV is more interested, or there's more critical things about the current in there. So we go from top to deep into the tank, and from waves to mainly current over the next approximately a little bit less than an hour. So start with the floating cylinder. Why a floating cylinder? Why do we need this? There is an energy storage concept invented by my colleagues from Innsbruck in Austria. It's the buoyant energy concept. It's a hydropower plant for the ocean. You can have a big floating device which is filled with water, and when you want to store energy, you pump the water out of this device, and if you want to release the energy, you let it flow backwards into it. And the nice thing about this concept is that nevertheless, in which status the big battery is charged, it will always have the same pressure head from the outside to the inside water level, which is absolutely crucial to have optimum conditions for pumps and turbines. So you can bring the best from a big hydropower plant, which have optimum and runs at optimum height into close to the floating offshore wind turbine to store their energy. But you think about, okay, it's a big structure filled with water, sloshing. Yes, sloshing is the main topic. And when you think about sloshing, you find tons of papers out there, which is from a hexapod, really sophisticated, up to 2D, quite simple solutions, and also for large structures. You find a lot of papers in there, but so there's a lot of literature about this, But if you merge it, the literature is not so wide, but yeah, obviously ships. So big tanker ships with LNGs, they have big tanks in there, and they're floating around, and they have interaction of inside sloshing and a big structure. And when you look at the design of those devices, you see that they have interaction with CFD, scale model tests, and the sloshing. But the problem is there are a lot of input values. Just imagine a whole form of a ship. It's really complex. And the geometry is quite hard to generalize it. So there's more specific solutions out there. And the filling levels are really different, and you have far more complexity in the different arrangements. And overall, it's quite a good, strong optimization process needed to integrate everything together. And state of the art that you use this integration, but you make this normally in iterations. So you decouple the sloshing element and the motion ship element. The use for both are quite good software solutions and modeling approaches solutions available, but they focus more on the pressure of the wall, also inside of these tanks, because this is the critical one. So in a ship, even if it's have a can have a slightly influence in the control of the ship, but the main issue of all of these investigations is about the pressure in the tanks, which is critical that you have to design how thick the walls of this tank should be. So from a very, very complex thing, we thought, okay, do we really, the floating storage will not move normally. It should stay in the same location, but it has also wave floats. Do we need really this full, this high sophisticated, very complex process, or can we reduce it? And we decided that to really have a good comparison, a good way, we decided we want to make a benchmark test. So why this benchmark test is to reduce the complexity and see what we really need for a numerical tool to get into to optimize it for the floating structure. And the simplest one is just to have an outside water level, an inside water level with a reaction. And in between there's a structure. And then it's just L form, but if you think about 3D, it's obvious that the best way to do this, or the simplest way is to do is a cylinder. And you observe the motion of this body floating in there in all 6 degrees of freedom. And with this data set, you can have a good benchmark test for your numerical model. And what we absolutely wanted to have from the beginning was we wanted not to have only small motions where you can stay in the frequency domain, because there is a lot of literature, or there is some literature around that it's not so critical about the influence of the sloshing. We wanted to see real big motion. So we wanted to have a challenging benchmark test. And why is it challenging? If you imagine that when this wall here in the numerics and moving walls, you have always have a lot of options, but you have to either adapt your mesh to the new geometry every time step where you refresh the geometry, or you have to adapt the geometry. So it's some software solutions use a fixed numerical grid and they adapt the geometry onto the grid. or you use a completely different system. SPH would be an option. So there are solutions out there, but the question was, how good are you? How good are you to solve such a complex or simple problem here, wherever you want to stand it? And so we decided to decide experiment, and we decided to compare solid and fluid ballast options. On the left side, you see the cylinder now filled with a solid ballast, so there are some crosses in there. They have the same velocity, the same density over the height, and like a water filling in there, which you can see on the right side. And on the right side, you see the cylinder, which is a 0.5 meter wide, 0.5 meter high, on the raised floor, and on the left in the floating in there. And you will see in the next slides always this S marks the solid solution, and the F, the blue one, marks the fluid ballast option. We investigated 4 different drafts to see in there to have a good overview of what the different start would be in influences of this, depending on this. We spent a lot of time thinking about the mooring system. It's quite critical in the tank that you have a good mooring system. And we decided that we use a very soft one, because we want to have a high degree of freedom of the motion of the cylinder. So in theory, you could just fix it in there and run all the waves against it, and nothing would happen. So we wanted to really have a really soft one, and we choose after one 4 mooring lines which join together in one point. So you have a lower resistance of the mooring around the pitch. So when the wave comes, the model or the cylinder moves really, really easily in this way, in this direction, and in roll a little bit less, and in yaw and all the surges is a little bit stronger limited. We used hollow elastic, which is quite fantastic. We started with this model, and we reused this elastic fishing device, fly fishing device supply for a lot of other mooring systems. So maybe keep this in mind with you whenever you have to design one. They are really good. So we talked about the different mooring, or what the mooring looked like. We made some natural frequency tests. You see here in the top one, that's surge, sway, and heave. So X, Y, and Z motion. And for all the 4 drafts here, surge and sway is quite low frequency, so it moves really slowly in the tank when you accelerate it. And quite interestingly, in heave, you could see no difference, nearly a little bit of a change in the if it's heavier, if it's deeper down, the natural frequency goes down a little bit. Yaw is quite small. In roll and pitch, what was the thing which you previously said about the asymmetrical use? You have this change here. You have a little bit of higher frequency in roll, but in pitch is a lower frequency. This is due to the asymmetry in this. But what you see here clearly is there is a big difference. The solid one stays up here slightly under 0.9 hertz, but the water goes with the same mass, the same velocity, same density distribution over the height, goes absolutely down. So you have a significant influence of the sloshing inside of the water. Just some pictures or videos of the actual element in the tank. You see, when you have to look really closely to see that there is something going on in the tank. The tank is 25 meters big. The cylinder has a 0.5 meter, so we have a really good wave field in there, and a small testing device. We have to search for it. We use 5 wave gauges in the front and 2 in the back. The new data set uses 5 on the back. And we run waves from 0.3 to 1.1 hertz with a wave height, with an amplitude of 5 centimeters, or a wave height of 10 centimeters. And Tom also mentioned, previously mentioned it, we used the upper water quality system. So in the first example, I will only use the upper water quality system. And on the right side, you see these markers moving around, and we capture these markers and detect the motion of this one. Just a quick insight into the examples. I won't go and search and sway, but only the heave options. We have these 4 different drafts in 2 different versions. The top one will be always solid one, and the bottom one will be always the fluid one. We have a heave. Previously mentioned, have a wave height of 5 centimeters and a heave of up to 10 centimeters. So a row of 2, so it's the motion is doubled as the wave height goes on. And just to keep this, move everything, the results together into one graph, all the 4 drafts into one picture, or 2 picture, and standardize it. Here you see now the row, which is quite obvious that you have come up to 2 for both cases. And when you look at the comparison with the natural frequency of the mooring lines, you can see, okay, deeper down, 1.7, we have a lower response frequency, and the peak is lower down here in the 0.7 frequency, and the upper one is 0.9, the higher one. So it's absolutely clearly defined by the mooring system how this react. But key thing is there is no big difference in heave for solid and fluid. It would be boring if this is all the same. So pitch, we get into the pitch. So then that's the rotation. When you look into the waves, it goes from front and backwards, which is the main part. And we were really happy when we are set up. We got up to over 20 degrees. So the pitch was really good. We had big motions. That's what we wanted to have. But if you look at these small lower draft with the fluid one filled, you see that there's something strange going on. And that was because when the fluid was the lower version of them with the water ballast, the model just hang into the wave and didn't move really far, really quick. So this was a strong dampening, and we were a little bit frightened that when everything goes like this, it would be quite a boring experiment if we see nothing. But when you look at the comparison again, you see that the solid and the fluid one, they had quite good, both when you go in the higher drafts, you see a higher response of them. Again, compared with the natural frequency, you see that the pitch has in all different load drafts were quite the same, and you see this grouping of the results in top of them in the pitch. But when you look at the fluid ballast option, you see that these resonances of the natural frequency was quite down, quite low, 0.5, 0.4, 0.5. And you see again these responses down here, which we didn't in detail investigate because we were more interested in the higher frequency bandwidth. But you can see that exceptionally with the smallest draft, everything else got the first peak here. And in addition, a really nice second peak in the top. So you see double with the frequency of the natural frequency, a good response, a big response of it. And also, it's not so clear as the top one, but it's quite interesting because there is something going on in this violet part here, which I marked here on the top. Just keep this in mind for the next slides. So there is something going on, which is strange because the response goes up and falls down quite heavily. So looking at the second rotation direction, that's the roll direction. Again, when you look at the top one, is the solid one. We have quite small roll motion, which we expected because so the waves go into your face, it goes the sideways. So that's what we expected. That's what we wanted to have. But what we expected, we didn't really expect, or I didn't really expect, is that we will have such a big roll in the fluid version. So there is something going on which is interesting. So we can identify a really big difference between solid and fluid for this higher frequency bandwidth, and there is a roll going on. Not for the lowest version. There is, said it's the boring case, but all the other ones are really quite interesting and nice. And when you bring this back together into one, each in one graph, you see the solid ones are quite boring again. They have small angles, small responses, but the fluid ones, they have these nice peaks again in the higher frequency range with roll. And when you compare this is again with a fits to the roll motion, to the natural frequency, and exactly there where the pitch, this is the small picture on the right side now down there for the water ballast, where the pitch goes down, the roll starts. So the water version, there is a shift between the roll between width, demand pitch into roll. And we did some investigations further into this and see that it's really it's parametric rolling, and that's sustainable, and it's remains for all the cases, and not artificially investigated it. So on the right side, hopefully you can see this quite interesting behavior. So the waves come from the left, from here down, flow in this direction up here, and the cylinder moves and rolls in side by side, and you see that it's even that moves out the mooring lines, the soft mooring lines out of the water, which is was quite surprising for us in the first moment, that because the easier movement would be from the side, so it's a really dominant motion on the side. We published these results, or previous results of the cylinder in 2 papers. The first paper, which is here, looking at the wave gauges, which is here included in the cylinder to measure it in the water level. And we have integrated some motion capturing system, adapted the motion capturing system to measure the water inside of the cylinder by using floating balls in there, which will be done in the future for the real tank experiment. And for these results, which I showed you, they are now analyzed and published, and you can access them and use them as a validation experiment. We also currently have under review a second paper where we looked at different wave angles and go into further why this roll motion is generated, and to be sure that we don't artificially introduce this based on our mooring system, and we can honestly say that this really definitely not a case based on our mooring system. The mooring which we use here is more restraining it, not provoking it. And the next step is obvious, where we'll try to measure the velocity in the inside of the sloshing, so that we can provide also velocity data to understand the sloshing inside far better, to how it generates this motion. Okay, so coming from a really basic research part to a more applied one. Tom previously mentioned it. We have more and more floating wind turbines to investigate in our facility. And the question is always, why do we do this? Can't we do this with the numerics? And I say, yes, you can do a lot with the numerics, but you also need validation. We do a lot of validation experiments to validate the numerical results. That's typically done with the final tests at the final geometry or close to the final design, because Flowy is not cheap facility, so you don't do it for just to have a first glance. You come to us with your final design, and then we test it and hopefully show that it works fine. In general, there is floating wind turbine. You have the problem that you have to combine 2 different worlds, the wind and the water. And in the scale model, you have to use different scaling laws for this. So in the wind, you have to Reynolds scale it, so you have to have the same Reynolds numbers and in the numerical and in the experimental case as in the in nature. And in water, you have the same food number. Okay, first we'll say, yeah, fine, two different scaling models. That can be challenging, but if you look at the different factors which you have to use, there is a big difference. So I'm coming previously, I did a lot of experiments in pipes, which you also have to use the Reynolds number or the Reynolds similarity. And when you look at the length scales, so if your model is 1 to 50 or 1 to 100, it's the same, but forces are quite different, times are quite different. So you have two different times. You would have a different time for the wind and a different time for the water scaling down, and also the discharges would be more for the pipe flow interesting. So, but mainly here is the forces and the time which are challenging. And we want to investigate it in the fluid similarity. So you have to bring down the wind simulation into our fluid similarity and to run it. You could do both, but if you have both, then it's getting really, really complicated, because when the wind generates different waves. So mainly you do this to when you look at the hydrodynamic performance, you simulate the wind load in a simplification. And yeah, how do we do this, and what do we do therefore? Yeah, you have, for example, 3 blades, which is quite common. Oh, before I go to this, I just wanted to say, why don't you talk about all the things are underwater? The things which are underwater are brought in from our clients. You saw some examples from Tom presented, but in this case, it's a company called Access Energy Projects, which developed this special device in here. And I don't want to touch onto this, but if you want to have a look at how it works, it's quite sophisticated. You can have a look at the homepage, and there's also a YouTube video about our testing campaign, which is more focused on that's what they wanted to present to you. And so I want to limit it to things which we contribute to this model. So yeah, okay, back. We have 3 blades, and each blade has a load, and it's distributed over each blade, and you can summarize this in 1 point, the third of the blade length, and you have 3 of them. And when you sum this up, because the blades go together into the shaft, into the center and the axis, and when you just sum all these 3 forces together, you get the center forces. Okay, that's quite straightforward. And when you look at the lever arms of each one, you can see that in every time step, everything is balanced. So for the system, the approach with 3 different forces would be absolutely similar to 1 big forces in the center. That's for a perfect system. And normally, you have a perfect system and everything is fine, and you can run. So with 1 point in the center force is similar to the 3 points on the blades. But yeah, we know that it's not always a perfect system. You will not always have a perfect system, especially with the floating wind turbines. They are getting more and more. They have at the moment they are talking about an exponential increase of different versions which comes out. There are different technologies in every parts of the world they are installed, and if you get more and more of those, the chance that something happens is high, or it's get increasing. If you have more and more, you will have the chance that it increases. And therefore, you should also have a look at the imperfect systems. Imperfect system could be that 1 blade is not precisely manufactured, or it has a little bit of a damage, or in worst case, a blade is completely damaged and has an influence on this. And the idea is how implement imperfect systems into the load bearing. How does the floating structure react on it? And in future, how does this device survive even a complete blade loss, or they have a problem in there, or will the complete system sink or fall over. We have to build up a prototype, a very special one. You see here again the tank, and the two different options. We have one, the center one, which goes out like one center force, or 3 different small forces. So either we use either this one or the other one. And for the central force, we use the winch. On the right side here, it looks quite fancy. It is quite fancy. Tom spent a lot of time designing it, and it worked really, really well. We were glad, and we think that's a really valuable device, and that's the gold standard for us. And we used for the main client testing, we used this as a device. And we could really give these forces which we need really good into the center of the hub. And then this is the other new, novel, slightly crazy approach, is that we have this spinning carbon fiber rods and 3 different jets of water. There are jets where water is pressed out of it and generates thrust, which is without the winch, obviously, and just the jets. I have to stress even more, that's just a prototype. We did this now, and we are looking forward to make this more resilient and more stable and more flexible, and to use this further. But it was just first system which worked. What did we do? We ran the complete model. Currently would be without everything, considering the wave, considering the wind. So we would only run waves and current and the winch. So these weren't the first and the last one. This is the typical case which we run for the clients. And because these clients, they had a research project and they wanted to see in this, go into more detail in this imperfect loads. So we included rotating, so that we just spin then the rotor blades, the carbon fiber, and have the winch inside, or with the winch inside there, and rotating in jets, which is the new standard, or the highly sophisticated one, where you push out the model back with the water jet, and only the jets, and as well, as previously mentioned, only the winch. We measured for all of these things the loads and the tethers down there. So they have more load tether than normally used, but each one was equipped with a load cell and motion capturing system. So you see here in the back the motion capturing system of the upper water, but obviously when you start thrashing around the water, you get in trouble that you can't see the markers anymore. And so we used also the underwater quality system, which is the blue lights on the bottom down here. You see this in the slides on the slide very well. And everything together, with all the things we did together for 2 different combinations. There were operation conditions, so where we have a high wind load and a low wave case, and a storm condition where we normally have a lower wind load and higher waves and current conditions. I hope you can hear a little bit of a tank sound that you see here, that the winch working. Just a small case, operational case. The winch pulls back the model here 5 to 10 centimeters and applies all these constant force independently of what the motion of the floating device does. Waves coming in. That's for us still the perfect condition, or the ideal condition, that you have this central force coming in there. And the more a little bit crazy one is the jets. So we have a high pressure pump in the tank down there, which pumps up water into this pipe, flexible pipe. This put into the shaft and distributed to each individual jet on the side of the model blade, and it pushes out the water and site. You see the water, here this water splashing. It's quite interesting to see this, and it was we had a lot of calculations before. Do we need a tarpaulin? Do we need something in front of it? We did last, okay. Luckily, we didn't need anything special because we have such a nice big tank, so it was fine for us. As stressed before, this setup is quite in an early stage of how we do it, but it works, and the paper is currently in preparation, so to publish the results. And I don't want to show you any further about this, and want to jump into the last topic of my presentation, and give you a little bit of an insight in things which we do in our testing campaign with the ROV. So ROVs are quite common, and they're getting more and more used around, and especially in offshore maintenance. It is quite critical to have them. And Orca Hub is a big research project or framework, I think, research framework, which joins together a lot of different researchers to bring up quite a nice opportunity to do some work. And they also provided us with the Blue Robotics ROV. So this is a commercial one which we tested here. Again, I don't want to say a lot about the ROV, which is in there, because first it's a commercial one, but the colleagues of us in the University of Edinburgh who are doing this project, they completely changed the brain of the ROV and the algorithm in the back, and made it completely new. And so the novelty is inside of the brain of the ROV. But for their algorithms, they needed to have hydrodynamic forces. Had to have how does the ROV react on wave and current, and that's very important for station keeping algorithms, which are critical to maintain and to observe, to do work in high current, challenging conditions in the sea, and also have data for validation experiments. Again, so all the three mentioned examples, all cylinder, the floating wind, and also the ROV are always validation. So we want to compare numerical data with our experimental approach. And in this case was also a main aspect for us, which is not always covered by the manufacturer, is that shadowing effects of objects in front of it. So classically, the ROV approaches a pipeline and it comes closer into the shadow, into the flow shadow, and then the complete flow conditions change for it. So we are looking at the forces which are acting onto the ROV based on wave coming from the top and from all sides with the current. And the first approach was when they came to us. Normally you do a towing tank. We do this in a towing tank. So you stick your ROV onto a carriage, and then you drag it through the water, and you measure the forces, which is quite common and very, very well used, especially for boats and ships. So there is nothing new in it, but it's challenging with the shadowing effect to have. And we were asked, could we do something a little bit more sophisticated, because we don't have a flume, we have this big circle tank. And we came up with an idea that we say, okay, why don't we hold this ROV just by tethers and a support structure in the middle of flow wave, in the middle of the depth in the tank center, and we have the possibility to run waves and current from all sides and have a really good impacting flow onto it. Plus, obviously, to measure the forces which acts on the ROV, we needed load cells. So, yeah, only 4 load cells shown, but obviously you need in total 8 load cells. to measure all the forces. And by having two opposing old tethers, you can have a pre-tension which you can remove afterwards. And you have now the chance to move, to bring obstacles in front of it and to directly see and measure the comparison. How does, when the ROV comes closer to a big pipeline, how does the ROV react or feel this change, even if it's have another closer or further away. So now you see here the blue ROV, the ROV hanging in there, restrained in the brake frame. It is a scaffolding frame, goes over the water surface and linked to the bottom. And each tether holds up the ROV, and that's in the center of the tank in 1 meter water depth. And you see here also this obstacle which we have on rails, where you can move forwards and backwards to simulate different distances and have them investigated and tested. These, just to have a detail of these load cells, they're quite standard ones for us. They were used here, 100 Newton load cells, as a good range of load cells. And in each load cell in the front, there was again 8 load cells around here, was also a marker. And these markers, just some are here blue underlined, they are captured by the underwater quality system. So previously we talked about, Tom mentioned it, the quality system, the upper water quality system. The upper water quality system works with infrared lights. So you have markers that reflect the infrared light back, but obviously underwater you can't use infrared light. You use just simple normal blue light, and these cameras, they send out the blue light, and this blue light is reflected by the markers and go back. And we have at each load cell a marker and a lot of markers on the ROV, not only one. We had 8 markers on the ROV, and in addition we had some markers on the cylinder to see where it is, hopefully that it's stable. And yes, it was absolutely stable in the construction hold, but it's always a little bit, when you have something sticking out, it can be challenging with a higher flow speed. Okay, testing. We tested the ROV in the tank with going down. Now here you see the model sink, the floor pulled down. We tested 3 different distances. So we have 0.9, 1.3, and 1.7 meter distance. That's a distance, the difference between each one is 0.4. That's the diameter of the cylinder, which was chosen, so it's just a representative one, and 0.9 is quite close. This is one of the far further ones. You see that all the cables are going into the frame and up to the gantry, and also the ROV has also a steering cable which is mounted onto the frame, so it's not floating around. It's quite consistent, so we don't have a different, always have the same influence of this cable in there. This is one when the system is running. I will show you a video in a second. From the top view, the ROV is quite in there in the center, and that's what really the advantage of this system is. You have the ROV in the center. Obviously, yes, you have a little bit of a wake, which is caused by the support structure. But you have to keep in mind that we tried to bring it as far wide out of it so that the center core where the ROV is not influenced, and we could get really good results of it and have good measurements of it. What did we do? Yeah, Tom mentioned it before. We have the chance to run all directions, 360 of wave and current. In this case, we limited us to the main direction, so coming from the front, which is the main cases, also with the obstacles in front of it, and ran some velocities from 0.2 to 1 meter per second, and from the side and also from the back. So we have a little bit of a validation of the results, and the RV is not fully symmetrical. So there is a just based on the geometry, there is a difference between these different directions of it. Waves will only run from the front with current and regular one and irregular one. So this was just a little bit of a peek into it, but the main thing was the current. Sorry, quite loud. Quite loud is realistic. Just switch off the sound. As Tom mentioned before, current looks in videos are normally really not very dramatic, but in reality, 1 meter per second is quite fast. So there is a lot of going on. What we did with what you can see here is in the underwater camera system, which is in this case we only had 4 in there. Now we have 2 more. And these 4 camera systems, qualities cameras, measure the motion of the markers on the ROV. And if there would be an obstacle in front of it, also would measure the motion in the, hopefully the not motion inside of the obstacle. In total, everything went well. We had a good testing campaign. The results were really interesting and good. And for this project, it's OrcaHub project, we already published the data set. So whenever you are interested in having the data, what the measurements results look like, you can have a go at our data share system from the University of Edinburgh. The data is now available. And what you will find in there is one data set, which is the raw data, which is just the load cells and the motion capturing system of the ROV, the different states. But also in a second process data, you find for each of these mounting points where a tether locks into the ROV, you find the forces in F and X, Y, and Z in the specific tank coordinate system or the coordinate system the ROV guys wanted to have. So it's for a civil engineer, where Z goes down is always a little bit suspicious, but that's exactly how they use it commonly. And you can access this and have a look at it and maybe use this for your future work or whenever you're interested in this. Our analysis and the paper, which is connected to the data, how we did the data analysis is currently under review and hopefully getting out soon, and then you can have a look at it. So everything which I present is quite close to the last to the presentation here. The next step in this project will be that we go back, hopefully when we go back to the tank, we have some further open tank testing. So the colleagues, they have now used their input, the input of the force measurement into their algorithms. They optimized the algorithms, and they, before coronavirus lockdown, they also had the chance to pre-test everything a little bit, and they had good results. And they go back now, hopefully when tank opens again, and do some more tests in addition with the current on, because previously they only run still water tank. So that's me. I just want to give you a quick summary what I just showed you. Initially, I started with a floating cylinder, which is a validation experiment. That's really basic research. We just want to do something very specific to solve a problem, which is hopefully solves another problem in the future of the energy storage system close to the wind turbines. And here was the thing which we want to give you with the validation data is available. It shows really big motions, which we wanted to have, which is quite nice and can be useful for when you're interested in fluid structure, fluid interaction. The data sets are available, and you can have a look at them and use them for your numerical codes or for your studies. Then the next step was a little bit more, I don't want to say crazy or not so crazy. It's more very special. It was the water jets. So we successfully used water jets to generate thrust each individual blade, which is not the thing which we want to promote as a replacement of a winch, but we want to see this as an additional tool for very specific investigations, looking into failure or imperfect system like blade problems, or in worst case scenarios which are catastrophic. And the third one was the ROV. Key sentences, sometimes less is more. This means that we use these very thin tethers, which were really strong and stable, but we could show that we can use a very support structure which is far out, not obscuring the flow, and fully use the capability of the flow wave testing tank to have this ROV tested in a really comprehensive way. So, and again, from top to deep down into the tank, from upper water quality system to a combination which is needed because of the water jets, down into the complete submerged system, where we have to use underwater quality system, and could use it very, very successfully to do this. Tom mentioned at the beginning, or the first picture of him, his slide was the slow-mo guys. I have now also wanted to mention that we didn't discuss this before, but it's really cool. So if you're interested in the flow wave the facility, and not the things which are so fully researched things, then maybe have a go at slow-mo guys. You either find them via this link, or you search for them, slow-mo guys and flow wave, and you find a really fun video which I already think close to 50 million people saw, and they did some things which we will definitely never repeat again. And I will see Tom thinking about this, what he definitely never will do this again. And also I want to mention second part where you can see Tom speaking about flow wave. I want to thank you for your attention. If you have any questions further, which are afterwards not mentioned or called, please drop me a line. If you need the papers, or if you don't find the data, I'm happy to help you. And that was my thing for the lockdown. I finally joined Twitter. So if you're interested in my Twitter account, here's my Twitter link. And with this, I want to say thank you, and I'm looking forward to your questions.
Thank you, Roman. Was really, really nice presentation, and you are doing a lot of interesting things over there. So right now we will start with the questions. So you can just raise your hand, pueden poner la manito, and I can translate the question if you want to do it in Spanish. So let's go for these questions. I will look into the. Okay. Meanwhile, the people are starting to think the question. I will ask some questions for you. For Tom, can you explain me how do you absorb the waves? Because you have some paddles in both sides. You make it actively controlling the paddles, or you have some other method of absorption?
Yes, it's all active absorption, so it's all force controlled. So rather than give a time series of paddle position, if you want to imagine the paddle is moving, rather than asking it to drive to a certain angle, you're asking it to produce a certain force. So there's a force transducer and a closed loop control in the wavemaker itself. So therefore it can also absorb the wave, but also absorb any reflections or sort of radiated waves coming off the model. It becomes quite difficult in a circular tank because you have to deal with the fact you don't want to absorb all the best way of describing it is I think the direction is also important. So you need to understand this is effectively a predictive control that says this is the force you expect. And the force control, the active absorption, is basically absorbing the difference between what you expect to be sensing and what you actually measure. And it actually makes the timing across the tank very important. So there's a sort of it's quite difficult in a circular tank. That's why there's not circular tanks, basically. But yes, once you've mastered it, it lets you do a lot of other. It lets you do all the fancy stuff with directional control and so on. So.
Okay, and how good is the absorption? So,
in energy terms, it's around about 97%.
okay.
We see in height, though, that doesn't quite. You get about. You usually get reflection coefficients below 10%, but it's a little bit different from a conventional tank because usually your absorption is better at high frequencies and worse at lower frequencies. With active absorption, it's reversed. So we get very good low frequency absorption. So we're very good on energy, but you tend to get more reflections at high frequencies. So if we know we're going to have a lot of high frequency energy, we also can put in foam beaches into the tank to absorb some of that.
Okay. Yeah, no one has raised his hand. So one more question to you, Tom. What is the range of the current that you can produce? How is the maximum current?
Okay, so in commissioning, we hit 2 meters per second, which was quite scary. So that's, but the tank was only designed for 0.8 meters per second. I didn't cover the design stuff in my presentation just because of time, but there was a lot of CFD work and experimental work on the design of the what we call the turning vanes. And actually, I might, if I have it here, I might be able to put up an image. But there was a lot of work that looked at the way the current interacts with the wave makers. And so a lot of that design was based on 0.8 meters per second. And because we weren't really sure, quite a big margin for error was built into the system in terms of power. And we were actually at the low end of what we expected in terms of losses, because the tank is basically designed as what you might think of as a low impedance circuit. So the idea is you're having minimal flow conditioning where possible. The design of the propellers is designed for very high speeds, and it all relies on the fact that you don't have much impedance in the system, so you're not putting in very heavy flow conditioning. And that's because we're not looking at very low turbulence intensities. A lot of those flow conditioning effects are to reduce turbulence. So what we did was essentially allow it to flow very freely. So actually we get to about 2 meters per second, but realistically, we don't go above 1.6 because it gets pretty ugly up there.
Yeah.
And above about 1.2, it starts to get a little bit scary, and the electricity bill gets very high. So.
Okay. One question for any of you, because I guess both of you knows the answer. How do you do in relation with the scale of some terms that you cannot scale? I mean, like some surface tension or some forces that you cannot scale. How do you manage that?
I'll answer the first part, because I think Roman can mention about because actually the turbine's a good example, because you have Froude scale and Reynolds effects, which Roman can mention. But usually you're relying on the scale. A lot of these things, it's because you're at a large enough scale that it's not too important. So surface tension, for example, at 20th scale, 25th scale, generally you're just trying to be big enough. Some of these scale effects don't matter too much. If Reynolds scaling is really important, for example, everything's Froude scaled in the tank. The good thing about things like tidal turbines at the scales we're operating at, okay, the Reynolds number is certainly not scaled correctly, but you're operating in the correct regime. Whereas if you go down to 100 scale, not so much. You struggle. I'll let Roman can perhaps, if he's happy to, without putting him on the spot. I'll give him a chance to answer on the wind energy side.
No, that's absolutely exactly what Tom said. In the Reynolds scale, I know not many real Reynolds scale models. You typically go there and say, okay, jump into the turbulent sector, and then you make a variation and say, okay, hopefully your results are independent of the Reynolds number. That's quite typical when you have pipe flow conditions, which I mentioned. Then you can't, all phases for high head power plant, you cannot really, you should Reynolds scale them, but you can't really do this in most of the labs, so you have to have such a small scaling factor, like so small model that you can use it, then you use extrapolation and use different Reynolds numbers to get it up. But normally the fruit scaling is really well known and it works fine. There is some limitations, we know, yeah. And you mentioned one is the reflection is always an issue with a tank. But you can provide really good data, and you see that I try to stress this, that the combination of numerics and scale model tests are really important. And I believe that this will remain, even if the numerics gets better and better.
Yeah, I think that are my questions. So if anyone has any more questions, I think we will just give you an virtual applause for both of you. Thank you very much for your presentation. It was really, really nice. And I hope we continue collaborating between the universities. And if you want anything, you are always welcome to ask us.
Yeah,
so
thank you.
Thank you, everybody.
Thank you very much. It was a pleasure to be invited to speak on this. So yeah, it's our pleasure.
Yeah, if you want a copy of your presentation, I can send it to you. We recorded it.
I don't know if I would watch it, but it might be nice to have it.
Okay. So we will continue with our next speaker. So thank you very much, Roman and Toman.
Okay.
Thank you again. Thank you.
So let's see. No sé si es que ya llegó el siguiente expositor, Rodrigo. Entre tanta gente aquí me es difícil.
Todavía no, dame un segundo.
Okay, entonces a toda la audiencia les solicitamos que se queden en esta reunión, ya que modificamos los links. Y la idea es que apenas llegue el siguiente expositor, que sería la 10:30, empezamos con esta presentación. Así que pueden esperarnos un par de segundos para empezar. Como Rodrigo mencionó, esta charla no será transmitida por YouTube, así que la gente que está en YouTube les solicitamos que se cambien para acá. Por temas de confidencialidad del expositor. Así que voy a terminar la transmisión ahora en YouTube.